For our next talk, we have Richard Rowland speaking to us about why Hello World is a massive operation.
Hey, good morning. Thanks for coming here today. It's a great honor for me to speak here because there's a lot of distinguished guests speaking and a lot of serious attendees as well. As a matter of fact, Guido van Rossum is here. And that's why I have an existential crisis, because I'm going to explain how CPython works inside and out. And if the inventor of Python is here, he's probably going to know how it does work inside and out better than I do. But it's still in that case, let me try what I could do. So, icebreaker, because it's a little chilly in Vancouver. I come from Tokyo, Japan. I'm a little jet-lagged. I work at OKCoin Japan, a global cryptocurrency exchange. Hobby, I like taking photos. In my back in college, I created a method to semi-permanently store data in a blockchain, a P2P network on GitHub. I implemented that using Python, and that was when I started getting interested in how Python really works under the hood. So I'd like to introduce you to how Python programs are executed, how your Python code is transformed into what's called an intermediate representation, and how that intermediate representation is turned into a bytecode, and how that is executed inside what we call a virtual machine, or VM. Now, to warm up the stage, let's have a question. What kind of language is Python? If you think it's compiled, please raise your hand. Okay. If you think it's interpreted, please raise your hand. We got more hands up. Well, that was a trick question, because it's actually both. Now, let me explain to you why it's actually both. But before we step into that, we should talk about the different models of program execution. First, we have compiled. We generate CPU instructions on the go, from the start, and then we execute them. As we all know, the C language is a very famous example. Then we have the interpreted languages. We start executing it, we fetch the source code, and then we generate the CPU instructions to run those instructions. Famous example other than Python is JavaScript. And then there's intermediate language, which generates the bytecode and converts that into CPU instructions for the virtual machine to consume. Another famous example other than Python would be Java. And as a matter of fact, Python comes in many kinds of flavors. When we say Python, we might think of the standard CPython distribution, but Python is actually implemented in many ways, including the C language, Python itself in PyPy, Jython, which uses a Java virtual machine, and IronPython, which uses .NET. Now, I'm not exactly sure about the origins of these use cases, but I could imagine that in certain organizations and scenarios, you would want to run Python on a different kind of runtime. So these alternate versions of Pythons were conceived to merge those requirements. For the presentation today, we'll be focusing on CPython. So, what is Python? Well, it's a programming language specification, and it's a program execution environment. So we know how to write Python, and we know there's a way to run those Python code. Now, what we're usually familiar with is the programmer's concern, how we write Python correctly, and how we implement the algorithms. What Python is concerned about is how we make sure we get the input, the source code, and turn that into something that the virtual machine can run. So in CPython, there are several features to take the source code and make that runnable on a computer. There's a lexer tokenizer, there's a parser, there's a compiler, and then there's a virtual machine. Let's see how these go together in an execution flow. So here's the execution flow. First, we have the source code that the coder has provided. That source code is, I guess, structured by this thing called a tokenizer. And we get this thing called the concrete syntax tree, or the CST. Now, the CST is a little too specific, so we try to make it more abstract. And that's done by the parser. The parser looks at the CST and then spits out the AST, or the abstract syntax tree. Now it's ready for compilation. The compiler looks at the AST and say, okay, let's see what we could do in bytecode format. And it spits out what's called the PYC, the bytecode. Now, this bytecode is finally what gets fed into the virtual machine. And the virtual machine takes that and converts that into CPU instructions. Now, it may seem a little complicated, but I would imagine that the merits of using a virtual machine approach is that it's more adaptable to many platforms. Let's say Windows, Mac, Linux, BSD. When you have a virtual machine, you have a layer of abstraction that handles the different specifications of the underlying machine. So first, let's talk about how Python code is taken and turned into CST. So Python code is taken by the tokenizer, and token is basically the unit of text, or the chunk that's recognized by the program to control the flow. These texts are defined as grammars, and the tokens grammars are defined in the CPython source code, the grammar and grammar/token directory. So here are some of the list of the tokens. We have end marker, name, number. We have the parentheses. We have await async. Basically, if you have a special keyword reserved, like say def or defining a function, that's a token, and that'll tell the tokenizer to recognize the start of a function or what have you. So how does a tokenizer work? Well, I think the best way to explain it is to see an example. So here we have a lovely hello world function, and let's see how a tokenizer can handle that. So you could just use a tokenizer by using the module tokenize. And here the output shows the nitty-gritty of the tokens. So in the beginning, it shows encoding. This source code is in UTF-8. The name, we start this thing called print. It's called a name. There's the parentheses. There's a string called hello world. And another parentheses, and end of the line. And if we actually look at all the CST that's generated from this, it's pretty long and detailed. As a matter of fact, these CSTs are nested, so you could actually make a tree out of them. And these trees indicate the blocks and the flow of the program. Now, you still can't really run a program out of the CST. So you have to first make it more abstract. And that's where ASTs come in. And in order to make an AST, you use what's called a parser. Now, there are several implementations of the parser. We used to have this thing called LL, but ever since Python 3.9, they renewed the implementation, and now it's called parser expression grammar. The specifications are defined in PEP, Python enhancement proposal. And when you look at these proposals, it's just like the request for comments on W3C. it specifies how a program or a protocol is supposed to work. So if you're ever curious about how internals work, this is a source of documentation that you could look up. So the AST is generated. When you look at the AST, it's definitely more sparse and more concise. It shows what's happening, such as calling a function, in this case print, and the argument being hello world. In fact, it's still a tree, so here you could represent it as a graph right over here. This tree was generated by Instavis. It's a module made by the team at Instagram, and basically some companies want to make sure that their code is running accurately as AST, so they do have tools to inspect the AST. Now, what we talked so far is a lot of things that happens on the compiler territory. And if you really want to dig into the compiler details, then these are some of the references that I would recommend. The one on the left, the Dragon book, is revered, and it's frightened a lot of computer science students, not only because of the cover, but because of the length. Yeah, but if you do tackle it like that brave knight you see on the cover, then you're going to learn a lot. But what I would recommend is crafting interpreters, because it does provide you a more concise overview of how a compiler works by actually implementing one in a matter of a few hundred pages rather than a few thousand. So now we have the AST. Let's compile it. So we call the PyCompile module, and once it's compiled, this is what we get. So the artifact of the compilation is in bytecode binary, and here we could represent it in hex. Now, because it's in hex, it's not really readable for humans other than the strings. You do see some readable fragments like hello world, but the rest is binary, so there are some letters that are not meant for human readability. But we could still try to decipher what these symbols mean. So let's look at what's happening on the header. On the first 4 bytes, it's called a magic number. And basically, the magic number, like with any kind of executable, identifies itself as being what kind of executable it is. When you have these 4 bytes, 610D, 0D, 0A, it says this is a Python program, and it was compiled with version, in this case, 3.9. The next 4 bytes is a padding. It's a series of zeros, and the rest is serialized Python code. If you want to learn more about it, again, there's another PEP that describes this one being a PEP 552. Now, in what part of the Python compiler is the bytecode generated? Well, it's generated in the Marshall module. And you could read the documentation in this place. If you want to look at the source code, it's the header is in the include directory, and the rest of the code is in the Python directory. Okay, so let's look at how an example hello world is transformed. Again, we have here the hello world that we all know and love. If we if we look at the dunder method code, we could see that it's stored as a code object in the memory. If we want the code to be output, then we could just use another method called cocode, compiled code. And here we have a string of bytes that shows the details of the code. Now, there's also more to the code. We have constants. In the Hello World program, we have none, and we have the string Hello World. We also have a thing called names. And here, the name here is the name of the function print, and that's the only name that's being called in this short program. So if we try to understand what's going on with the bytecode, the best way to do that is to read each letter. So in Python, there's this module called diss that we can use. And we could just say the first, if we look at the code that we have right now, the first letter is T. So we look at the what T is represented as a number. In Python, there's this thing called ordinals that turns alphabet into letters. And here you get 116. And what is 116? Well, if we look at dis.opname, and we get load global. So opname is basically a list of opcodes stored in the module, and load global is one of them. Let's talk about the dis module. It's basically for decoding the Python opcode, and it's included in the CPython. As a matter of fact, what is an opcode? Well, an opcode is basically a kind of instructions, a unit of instruction, and it's defined from 0 to 255. The whole list is included in the include directory opcode.header file. There's more information on the documentation, so you could read that. It lists the opcode and what they do, like the load global that you just saw. So if we want to learn how an Hello World program is operating, we could just list all the opcodes of the program. So here we call it dis module, and we call it dis function, and we call the program or the function. And here is all the opcodes that it utilizes. So first we have load global. It has to load the name. So we load up print. And then we load the constant. Here we have hello world. You remember the constant from the part of the constant list that we saw earlier. And then we call the function. You see, before you execute a line of instruction, you have to load the instruction. So that's why here we have the global that's being loaded, the function print being loaded, and then the argument being loaded. Then it's called. Then the result remains on the top of the remains in the program. So we pop that top. So this time it doesn't really return anything. So that's why what we load is none, and then we return that none value to the execution. Oh yeah, here it is annotated. So that's how a program works. And then we introduce the virtual machine. Well, what is a virtual machine? It's based on a stack. We'll talk about stacks in the next slide. Basically, the virtual machine executes the compiled intermediate language. And because it's a virtual machine, it's in between, it provides an abstraction and helps execute a single source code onto many platforms. So what is a stack? I'm sure many of you are familiar with the Tower of Hanoi. Basically, you put like blocks on top of each other, and you could only work with the blocks on the top. Python works with a similar structure like this. You execute with the data on the top. And I guess the stack model is different from a register-based model like LLVM. In this case, it writes into the array inside the memory. But let's get back to stacks. So how is the virtual machine implemented? It's basically a really long switch statement. And I know that long codes aren't encouraged, but but in this case, you know, a switch case really suffices, and it just works. The switch statement is contained within the Python subdirectory, the ceval.c file. And basically, it's just the switch and the target and the opcode name, and it just tells what to do with that opcode. We should also introduce the notion of an execution frame. It indicates the scope of a program. There's three kinds of stack in the execution frame. There's a call stack, there's the evaluation and data stack, and there's a block stack. So let's see how stacks works. Another good program to demonstrate this would be a factorial because it's recursive. Here we have the base case, and then we have the recursive instruction. So let's work that with the factorial 3. If we execute that program, first what we get is this. We have the main execution frame, and on top of that, we have the function, the execution frame from the function factorial. Now, in this program, it has the information as a data stack. 3, the factorial function, another 3, and another 1. And within the factorial function, we have n minus 1. So 3 corresponds to the n. And first we do the subtraction. And that's how we get 2. Now, on top of the stack is factorial function and 2. What do we do with that? Let's spin up another execution frame. So it stacks up on top. And here we have the factorial execution frame and 2. Well, this turns into factorial of 1. So we call that into an execution frame. And finally, we reach the base case. So this execution frame will finish executing and return the base case of 1. Now, on the lower execution frame, we have 2 times 1. We execute that and get the results of 2. So we return that to the bottom execution frame. Now, on the bottom, we have 3 times 2. We return that to the main execution frame. And that's how you get the result of 6. So what do we go over? We went over the Python execution flow. We saw how Python code is converted into an intermediate representation. We saw how bytecode is generated. And we saw what happens into the virtual machine. Now, if you all got interested, I think the best way is to learn more in these resources. You could always look at the Python Developer's Guide, which is meant for anyone who wants to make contributions or modifications to the CPython internals in order to let you make contributions. They give you a guide of how it works inside, so it's a very good guide. You could also ask the Python mailing list. Here are some of the mailing lists that you could use. Core Mentorship is good for beginners who want to change the CPython source code. There's also Python Dev, etc. If you subscribe, you always see Guido responding. So it's a pretty nice community, and I wish Stack Overflow was kind of like this. And then if you want to refer to some external resources, there's also Inside the Python Virtual Machine, a book by Obi Ikenosu. And another useful guide is CPython Internals by Anthony Shaw. This one's published by Real Python. So here I am giving a shout out to our sponsors because thank you for letting me speaking here, right? And so with that, I've given you enough information to understand how execution works. And that's why here I exit my presentation. Thank you for listening.